Okay, so now let's now that we have figured out what P1 is, let's also figure out what P2 is. And P2 is what? P2 is minus B over A, right? So if I know what is B, what is A, so if we simply plug that in, so what we'll essentially get is, and if we do some manipulation, some algebraic manipulation, so this is what we will get. In the denominator, we will get C2 plus CGD C1 by CGD plus C1. So if I go back here, so what I'm essentially doing is we recognize the fact that uh, we have this term, divided by the A term, right? So what we are essentially doing is we are dividing the numerator and the denominator by C1 plus CGD. Okay, so if we divide the numerator and denominator by C1 plus CGD, we are going to get this thing in the denominator, and in the numerator what we will get is GM5 times CGD by CGD plus C1 plus GDS5 plus, or like G05, not GDS, right? We're not using G0. This is G05 plus G01 times CGD plus C2 by CGD plus C1, right? So again, this seems to be a bit complicated, right? So we'd like to make sense of it, right? So given the fact that we were focusing on G0, on the pole associated with V01, right? Let's not use this. So here we have G05 and C2, and this is DO. So the earlier pole that we were the P1 was based on the pole time constant associated with the node V01, right? And when we were trying to figure out time constants, we can desensitize the inputs. If I desensitize the GM, so this goes off, this is no longer required. And what we essentially said was the P1 node, the pole P1 associated with G1 was whatever we got. Now what we are doing, what we are saying is that the pole P1 associated with, let's say, this node V0. Okay, so the pole, if we are trying to figure out the pole associated with V0, what we will see, the P2 will be some conductance by some capacitance. Now in the conductance term, what should I see? I should definitely see G05, and I should see some additional stuff. In the capacitance term, I should definitely see C2, and I should see some additional stuff, right? If I can express P2 in terms of some equivalent conductance, so essentially what we are trying to do is we are trying to see if we can express the conductance and capacitance associated with the node V0 to be of some G equivalent and some C equivalent. Okay, so let's see if we can figure this out. So what about, let's start with the easier one. Let's start with C equivalent. So what is C equivalent? C equivalent should be, at least C2 should be there, which is here, plus we have some additional term. And what is this additional term? This seems like a series combination of CGD and C1, right? So in this case, do you see any series combination of CGD and C1? Looking from V0, do you see any series combination of CGD and C1? We can see, right? It looks like there is a series combination of CGD and C1, and that is what that appears in the denominator, right? We have C2 and we have this, right? So essentially The denominator makes sense. Okay, but let's switch to the numerator. In numerator, I should have what? I should definitely have G05. G05 appears here. But what is the dominant term in the numerator? Whenever you have Gm times something, then you have to take notice. In this case, since all the capacitance we assumed are of the same order, then obviously that first term should be the dominant term. Now, what is that first term? What does that first term remind you? It seems like Gm has been, the conductance of Gm has been scaled by a certain factor, right? And the factor is CGD by CGD plus C1. So what does that remind you? So let's, for the time being, let's ignore. So let's ignore this G01 for the time being, okay? And let's try to figure out what is the impedance. What is the impedance of this node looking in, right? If I apply a V test here, right? If I apply a V test here, what voltage will appear here? This voltage will be V test times CGD by C1 CGD, right? If that voltage appears here, what current will M5 draw? M5 will draw current of GM5 of that times that, right? CGD by CGD plus CGS plus C1 times V test. So what will be the equivalent resistance or equivalent conductance? The equivalent conductance will be Gm5 times CGD by CGD plus C1, right? So that is what that appears here. So essentially the feedback around M5, is increasing the output conductance, right? You see that the feedback around M5 is increasing the output conductance, and that makes sense, right? Because at high frequencies, if P2 is supposed to be a high frequency pole, right, which was our initial assumption, if P2 is supposed to be a high frequency pole, then the conductance of CGD cannot be treated as an open circuit anymore, right? So which essentially means that any excitation at the output node part of it will seep into the gate of M5, and it will excite the gate of M5, and in turn it will draw a current, and that current will be in phase with the excitation, which means it's a resistive or a conductive. It's a conductance, not a capacitance, right? There will be a capacitance effect. The current through the capacitance will be there because of the C1 and CGD, and that appears in the denominator. Okay. Now you might as well say, why didn't we take into account G01? And obviously D01 we should ideally take into account, but again this is an approximation. Because we didn't take this into account, so this P2 approximation that we are doing is not exact, and because of that you get some extra term here, right? But fortunately that extra term is not dominant, so we can essentially say that that is because of that so many approximations we are doing. But the key thing to notice is that we are essentially getting an intuition or a hand behind the locations of the poles. Okay, so now if we assume that the dominant terms are Gm5, right, and dominant terms of C2 and CGD, C1 plus CGD, all these things, then what is P2 then? What does P2 become? P2 becomes Gm5 CGD by CGD plus C1, that is the conductance, and in the capacitance I get C2 plus series combination of CGD and CG1, the C1, right? This is great. This is P2. So what was P1 quickly? P1 was what? P1 was the conductance, which was G1, and the capacitance was the amplified version of the CGD capacitance, right? So that is 1 plus Gm5 by G05 times CGD. I'm neglecting the other terms. I'm only keeping the dominant terms in the picture. Okay, fine. But note that in our transfer function we also have a zero. So this is zero that we have been avoiding for a while. But what is the location of the zero? The location of the zero is that value of s for which the transfer function goes to 0, right? So what value of, for what value of s, what is the root? Root of the numerator, the root of the numerator is s equal to gm5 by cgd. So 0 is plus gm5 by cgd. Note that this is a positive half. This is a positive, this is a right half plane 0, not a left half plane 0, right? Okay, great. So now let's see, in the presence of cgd, in the, or rather let's see what is the effect of the poles and zeros in the presence and absence of cgd, right? In the absence of cgd, what was the pole p1? P1 was at P1 was at G01 by C1, and P2 was at G02 by C2. Approximately, if they are of similar order, they are close by, right? So these are in absence of CGD, right? So if we didn't consider CGD, so which means that the pole locations would have been something like, I mean, the transfer function would have been something like this. But in the presence of CGD, right? In the presence of CGD, we see that these approximations, I mean, these locations are probable, and not only presence of CGD, in the presence of a significant amount of CGD. I mean, CGD can be there, but can be very insignificant, but not that. In the presence of CGD, and CGD becomes significant, if CGD becomes comparable to C1, right? So if in the presence of CGD, where is P1? P1 goes from G01 over C1 to G01 by, I mean, there is obviously plus C1 term here. So this moves to the lower frequency. This moves further to the lower frequency, right? So it goes somewhere here, right? So it goes somewhere here. So this becomes a P1 in the presence of CGD. What happens to P2? A very interesting thing happens to P2. The new denominator of the P2 more or less remains same, right? Maybe the denominator is increased from C2 plus something, but what has happened to the numerator? The numerator is now a function of GM5, right? And if CGD and C1 are of the same order, the numerator is approximately GM5, some alpha times GM5. Earlier, the numerator was G02, which means that what? P2 has shifted to the higher frequency. The pole splitting is happening automatically, right? So we don't have to do much. The poles, by the virtue of CGD, the pole splitting has taken place automatically, right? So your P2 has come here. So which means that our transfer function, new transfer function will be, the DC gain doesn't really change. The new transfer function becomes a new, so new transfer function becomes something like this. Okay, all right. But now what about, now that we have a 0, what about the 0? Where do you think is the location of the 0? Again, if CGD, C1 and everything are of the same order, so clearly 0 is at a higher frequency than P2. So we'll probably have a 0 somewhere here. And when you hit a 0, what happens to the slope? So this is, sorry, I should sketch it properly. The slope gets restored back to 20 dB per decade, right? This is minus 40. This is minus 20 dB per decade. Okay, so good things are the pole splitting happens naturally. If the pole splitting doesn't happen naturally, you can put an additional capacitance. You can put an this is called the Miller capacitance. You can put an additional Miller capacitance to split the poles, right? But the bad thing is that we have a 0. Why is it a bad thing? By the way, is it a good or a bad thing? Is it a good or a bad thing? It's bad thing because it's the right hand side 0, and if it's the right hand side 0, what will be the phase at UGB? So the angle at omega u will be, what will be the angle due to P1? The angle due to P1 will be minus tan inverse omega u by P1, which is approximately minus pi by 2, right? Because P1 is anyway much lesser than omega naught, omega u. Then you will have minus tan inverse P2 by, omega u by P2. This is good because in the sense that P2 has moved to higher frequency than before, so this is even better. But now we have a right hand side 0. Since I have a right hand side 0, this gives me an excess phase lag. right? This gives you an excess phase lag of tan inverse omega u by c. So this gives an excess phase lag, which means this degrades the phase margin. Okay. So what I would like ideally expect is to move this 0 to as high a frequency as possible, but you see that in order to do that I have to increase GM5, right? It's good if I can increase GM5. It can also move P2 away, but increasing GM5 comes at a cost of more power, right? Because you have to burn a lot of power, you have to burn excess power at the output. So that is why people have tried to find out architectures where we can probably not use extra power, and let's see if we can cancel this right hand side 0, right? So how do we cancel right hand side 0? So by the way, what is the genesis of a 0? The genesis of a 0 is the fact that what is a 0? 0 is a root of the transfer function, right? Where the transfer function goes to 0. So in other words, so if I sketch this, we find out we have bunch of stuff connected here, right? This is V0, this is V1. So at 0, right, at s equal to z, V0 has to go to 0, right? That's by definition, right? So if V0 goes to 0, right, if V0 goes to 0, I don't have to bother about this stuff connected here, right? So this is equal to 0. If this is equal to 0, what is this current? This current is GM5 times, sorry, this current is CGD, SCGD times V1, right? Where will this current flow? This current will flow through through the through the M5 transistor. What is the current through the M5 transistor? This is GM5 times V1. So the location of the 0 is essentially the if you solve for KCL at V0, the value of S that you get is the location of the 0. So SCGD times V1 becomes GM5 times V1, which means S is GM5 by CGD. This becomes a location of the 0, right? So by intuition you can figure out the location of the 0 by simply by setting the output to 0 and solving for KCL and KVL. So whatever solution of S that you get will be the location of the 0, right? So now what we are looking for is to ensure that the 0 vanishes. It can be shown that if you I'll not get into the derivation of it, but if we put a, let's say, a resistance here, let's say put a resistance R here, let's call it RZ, this is CGD, right? So what if I use the same condition, what will I get? What is the current through this branch? This current through this branch is V1. At the 0 frequency, the current through this branch will be V1 plus RZ plus 1 by SCGD. This should be equal to GM5 V1, which essentially means that GM5 RZ plus GM5 by SCGD is equal to 1. So if RZ equal to 1 by GM5, then the solution is S equal to infinity, right? So in other words, if RZ becomes exactly equal to 1 over GM5, then the right hand side 0 vanishes, right? In fact, we can do even one better. The right hand side 0 causes a phase lag, but a left hand side 0 causes a phase lead, right? So if we make RZ to be greater than GM5, right? If RZ is greater than 1 by GM5, then what is the location of the 0? Then we see that basically solve that above equation. So we get 1 over SCGD becomes 1 over GM5 minus RZ. So this becomes S is equal to 1 over 1 by GM5 minus RZ times CGD, right? And if RZ is greater than 1 over GM5, then the 0, right, the 0 shifts to left half plane, right? So on the left half plane, 0 instead of giving a phase lag, gives us a phase lead, which means what? Which means uh, whatever you see here, this is minus tan inverse omega u by z terms, that in this case this will become plus tan inverse omega u by z, where I am talking about mod of z, obviously, in this case. So your phase, the total phase lag will be so angle at omega u will be minus tan inverse omega u by p1 minus tan inverse omega u by p2 plus tan inverse omega u by z, where of course z in this case is 1 by rz minus 1 by gm5 times cgd, right? So very often, that's why this trick is often played in order to improve the phase margin, right? So in a nutshell, what does the total final architecture look like? The final architecture of our two-stage operational amplifier is the following. So maybe we have a current source here, which was mirroring our transistor, which was current mirroring, right? So we had this, and then we have a CGD capacitance, but instead of CGD, if we have to put an additional capacitance, we can put the additional capacitance, let's call this CC. If the CGD capacitance is small, we can put an additional capacitance CC and put a RZ here, and this becomes a V0. And if we have to close the loop, all we have to do is connect this guy to V0, and this can be VCM plus VI. This becomes VDD, right? So note that this is a, if we go back to the first lecture, in the introductory lecture, and if you see that schematic of the op amp that we promised, right? So this is the schematic of the op amp, that this is the schematic of the two-stage op amp. That was the motto for this course, right? And more popularly, this is often when we say that we have a op amp of sine minus plus a, what we generally mean is this structure, okay, where the plus terminal is which one in this case? How do you know what is plus terminal? That the input terminal, which if I raise that voltage, the output should increase. So if I raise this voltage decreases, so this voltage increases. So essentially this becomes a plus terminal, this becomes a plus terminal, and this becomes the minus terminal, right? So when you connect anything in negative feedback, you essentially connect it like this, right? So this is the equivalence of these two structures, okay. So essentially we have kind of come to the end of the course, but before I wrap up, there is one thing that we didn't touch upon at all. I'll be amiss if I don't refer to it. We'll not be using it in this course because I mean, we essentially ran out of time, but we should at least know about this effect, and that effect is often called as body effect, right? So what is a body effect? As we saw that our transistor has a is biased on a substrate, right? Is biased on a substrate, or is built on a substrate, and it's not necessary that the drain the source and the body terminals will be always be shorted, right? It's not necessary, because if you have a cascode transistor, as you can see, the source is at a higher voltage than ground, but our body is always grounded, right? Our body is always grounded. P minus, this is always grounded. Okay, so since this is always grounded, there is a difference in voltage between the body and the source, which means that there is a reverse bias. This is a reverse bias PN junction that has that this is a reverse bias PN junction. Along at the drain side, you have a reverse bias PN junction on the source side, which we have kind of neglected, right? For the what is the effect of this? The effect of this, that there will be depletion region around the source, and overall the effect of this will be it will increase it will change the threshold voltage, right? So this changes threshold voltage, right? So higher source to a positive source to body voltage increases VTH. So if it changes threshold voltage, then obviously the transistor parameters change, but fortunately it doesn't change the threshold voltage significantly, right? It's only a small fraction of threshold voltage it changes, so that is why we kind of neglected it throughout the course. However, anything that changes threshold voltage can also affect our incremental model, right? So because our threshold voltage is a function, our current, your IDS is half mu n Cox VGS minus VTH whole squared. Now, if the threshold voltage, if the source voltage changes with the signal, right? So if Vs changes, then VTHN changes, then IDS changes, right? Which means that, or rather in this case, if not Vs, if VSB changes, this voltage between source and body changes, which means that the current there should, in the incremental model, there should be a term of something times VSB, right? So that is what is also used, and you will see the literature in some cases where on top of GMVGS we also have a additional current source. This is called GMBVS. Okay, so our transistor model remains whatever it was, but on top of that we have an additional current source. But note that if the source is always grounded, or if the source doesn't move, right, then VBS is essentially zero. For example, in a common source amplifier, the source is fixed, so the body is also fixed, so this doesn't come into picture, right? But in let's say a cascode transistor, if you have a cascode transistor, then the source is moving but the body is grounded, which means this will come into picture, right? So it's a minor adjustment of the small signal model that you should keep in mind. In this course, we will not solve any problems using body effect. but this is something that you should keep in mind when you are doing design, because your small signal parameters can change slightly because of this because of the body effect, right? So if we include body effect, what is the final structure of the MOSFET that we ended up with? So the final structure of the MOSFET now becomes, we have a capacitance CGS, we have a capacitance CGD, we have a capacitance CDB, then we have a GDS, right? So this becomes a drain. I don't need to use this because we are doing only the MOSFET model. This becomes a gate, and this becomes the source, right? So this is kind of a rudimentary transistor model that we often deal with. But now that we have gone through the entire course, uh, we know that it's not necessary that all the components need to be in place while doing our analysis. For example, if we are doing DC analysis, we can forget about the capacitances, right? So if we know that the source is grounded, for example, then the CGS capacitance goes to ground and it only loads the previous stage, right? It gets clubbed into the previous stage. Similarly, CDB gets clubbed into the next stage capacitance, right? So we can play around we can play around with these models, and we can make simplifying assumptions as we proceed, right? Okay, so yeah, so with that, it's time to wrap up the course. uh, I hope that we all learned something in this process. I hope you found this course valuable, right? So if there are any questions, please feel free to post your queries in the forum, and we would be happy to answer them. uh, my name is Iman Mondal, as you might know right now, and it's time to sign off. Thank you.